my TTL computer. Today we're going to take a look at the boot ROM capability that I was able to put together for our computer. And as we saw in our last video, where we demonstrated using the computer, it can be tedious and error-prone keying in the programs manually using the switches. So the key thing that we developed there was the hex loader, which gives us the ability to load in programs from our laptop into the computer. So the question remains, how do we get hex loader loaded into the computer? Because the computer comes up empty. So that's the genesis for the idea of a bootloader and a ROM, so that we could have some ability to put the hex loader in ROM and load that into memory. So as I considered that, the first thing that was considered was obviously using an EEPROM to store the hex load program in. And the EEPROM would be hardwired into the computer and would glue circuitry in the computer would hardwire the ROM to the first 64 bytes of RAM, and then the rest of the RAM would be dedicated for additional free program space. So the problem with that is that we're limiting 64 bytes, fully 1/4 of our 256 bytes of available program space, to the hex loader in ROM, and it's basically frozen out. We can't use it. We're really reducing the available RAM for programs by 1/4. So another solution would be that if we could load the hex loader into just random access memory, and then after a program loads in, it could basically take control of that RAM and use it for data area, or it could use it for the stack area for the program. So we wouldn't be completely losing those bytes that would be dedicated to the hex loader in the beginning to get the program loaded in. So that was really where I started to focus my thinking and what we could do to achieve that. And so the thing that was obvious and jumped out to me is that, we have some of our chips are implemented with microcontrollers. And this is really one of the key benefits in this approach, is that whereas these microcontrollers are really implementing in the solution, mimicking 7400 series logic or some other logic elements, and we're trying to really using them in that role. There's extra processing power sitting there that we can take advantage of if we are creative about it. So what could we do here? So we kind of have one element that's already wired up and designed to give us a byte when we request one, and that's the serial UART. So the approach I came up with was that we could use the serial UART in a special function as a ROM, where we could request a byte and it will give us the next byte in the ROM. And so that would give us a place to store the data. So how are we going to actually control calling that data and getting it loaded into memory? So the obvious contender for that is the controller, which also is a microcontroller. So the solution I came up with was this. When the hardware comes up, it's initially powered on, it will be in boot ROM mode, and that would affect and apply to both the controller and to the UART. So they'll come up in that state, and once the clock starts, that the controller will basically request a byte from the UART, and it will store that into the RAM. It will update the program counter, load that into the memory address register, request the next byte, load that into RAM, update the program counter. So it would go through that process and would eventually stop and have the whole hex loader loaded into memory. So that's the basic idea. That I implemented a first version like that, and then I realized that we could also have the boot process also set up our stack pointer for us. So besides loading in the hex loader, it will also set up the stack pointer, and our programs won't need to deal with dedicate any time or space in doing that. The bootloader will automatically do that. So we can take a look at how that works now. So we can, I have the system is up and it's in program mode. So what we want to do is disable the clock. We want to switch this to run mode now. We're in run mode. We want to reset our program counter. Reset our step pointer, and we're basically, oh, now this comes into the special reset for the controller and for the serial UART. We'll reset those. They're enabled now, so those are reset and come up in boot mode. So they're basically ready for the controller to request the first byte from the UART, load it into memory, and continue on. So what we have to do is enable the clock. That's spinning and it's done. So hex loaders automatically is already loaded into the system. So we can just verify this. We'll go disable the clock, go back to programming mode, and if we take a look at what the program counter is, that's 64. So that's loaded in the 64 bytes into memory. All right, so let's reset the program counter, reset the step counter, switch back to run, and okay, so the hex loader is ready to go. So okay, so we have our transfer program all ready to go here, which is going to hit enter. Okay, so that's started. That's just waiting for the hex loader to initiate the file transfer. And that's all just going to enable the clock. And that's going. We see our file transfer is proceeding. And this is just transferring up my TTL Hello World program. So that should begin in a minute. And there it does. Okay, so that's the process. That's our boot ROM process on our computer, and that's a huge improvement from having to key in the hex loader 64 bytes every time. We are going to do system development on our laptop. So this is pretty much right where we want to be, and I said opens the door to our software development, our remote software development on our laptop, and we can just rerun the hex loader here as many times as we want or need to. So we can just stop and run this as many times as we need. And we'll kind of see that process when we look at the laptop, the development flow in our next video. So that's it. Thanks for watching.